Alright, welcome back. This is the second video for section 5.5, and we're going to introduce a couple of new definitions. The first one is the definition of absolute convergence. So we say that a series is absolutely convergent if we take the sum of the absolute value of its terms. So if the sum of the absolute value of a sub n converges. If that converges, then the series absolutely converges. Now, what if the series itself converges? What if that converges, but when you take its absolute value, it diverges? Well, in that case, we call it conditionally convergent. It's not absolutely convergent, it's conditionally convergent. If it converges, but its absolute value diverges. And just one little note about a series that is absolutely convergent. This right here, so this first statement says that a series converges absolutely. So if it converges absolutely, then it also converges. This says a series that converges absolutely converges. We could just say it also converges. Okay, so example, let's see how this works. Example 2, determine if the series is absolutely convergent, conditionally convergent, or divergent. Well, the first example should be familiar because we just looked at an example like this in the last video. This looks like the harmonic series, except it's alternating, right? What did we say about an alternating harmonic series? We said that it converged by the AST, right? So first, n equals 1 to infinity, negative 1 to the n over n is the alternating harmonic series which converges by the AST. We already showed that that was the case, so we don't need to do that again. We can just state it now since we proved that. So the series itself converges. Well, what about, does it have absolute convergence? So if we say absolute convergence, so n equals 1 to infinity of the absolute value of negative 1 to the n over n. Well, what's that series equal to? If we take its absolute value, what's going to happen to the series? Well, the negative 1 to the n is going to go away, right? It's just going to look like 1 over n, which is what series? That's the harmonic series. Is the harmonic series. So if we try to show absolute convergence, we get the harmonic series, which we know to be what? That one diverges. So if a series converges, but its absolute value diverges, what do we call that? Again, up here in the definition, we say that that conditionally converges. We say, so our series is conditionally convergent. All right, so there's the first example. Example B now, we can take a look at, and let's start by taking its absolute value. So if we take our series and we take its absolute value, so you have negative 1 to the n plus 2 power over n squared, and if we take its absolute value, what are we left with? we're left with 1 over n squared. Now, is that a familiar series? What can we say about that series? This is something that you should all know how to do. This is a series that converges. Why does it converge? Okay, well, hopefully you said because it's a p series, right? It has that form of 1 over n to the p. This is let's note it. This is a p series with p equal to 2, which is greater than 1, right? Anytime our p value is greater than 1, we get a convergent p series. So this is a convergent p series. So the absolute value converges. Remember the last one, the absolute value diverged because we got the harmonic series. But in this case, it converges. So if we get a convergent, if the absolute value converges, then we can say it is absolutely convergent. So our series is absolutely convergent. Okay, so now you've seen one that is conditionally convergent. You've seen one that's absolutely convergent. Let's take a look at one that is just a little bit more complicated. So part C, we have the sum of sine of n over n cubed. And what makes this look complicated is because of sine n. What do we know about sine n, right? If we were to take a look at the graph of sine n, it kind of alternates back and forth. And what are the values of sine n that it alternates back and, or what are the values that sine n alternates back and forth between, right? Its peak value is 1 and its lowest value is -1. So sine will only attain values between -1 and 1. Now, which kind of gives us an alternating series, right? It's going to alternate back and forth between positive and negative values. Now, if that sine n wasn't there, what would this look like? If that was stripped away, if you will, wouldn't it just look like n cubed? Now, what do we know about n cubed? Well, that's just like the last example. That's a p series, right? So, and we did an example like this, I believe, when we talked about the comparison test in the last video. Could we do comparison here? Because we know if we were to take the absolute value of this, right? If we were to take the absolute value of sine of n over n cubed, well, the bottom is just going to be n cubed because n is always positive, right? It starts at 1 and goes to infinity. Any positive number to the third power will be positive. We can drop the absolute value on the bottom. We can't drop it on the top. And so now this is where the comparison comes in, right? Because if you were to compare the absolute value of sine n over n cubed with 1 over n cubed, we could say that the fraction on the left is always at least as small as the one on the right, because the biggest value that the numerator is going to be is 1, right? Sine of n, the biggest value sine of n can have is 1. So at its biggest value, sine of n will be 1. In that case, sine n over n cubed is equal to 1 over n cubed. But if it's any other value, sine n will always be less than 1, which makes the fraction on the right always bigger. And what do we know about the fraction on the right? Well, what do we know about its series, right? So n equals 1 to infinity, 1 over n cubed is a convergent p series, right? So p is 3. So that's a convergent p series. The comparison test works because we're smaller term by term. Each term is smaller than the terms of a convergent p series. So sum from n equals 1 to infinity sine of n over n cubed. That's absolute value converges by the comparison test. By the comparison test. And if it converges by the comparison test, then it is absolutely converges. Thus, the actual series n equals 1 to infinity, sine of n. So we now have the absolute value gone. If its absolute value converges, then the series itself is absolutely convergent. And we are done. All right. So you can go ahead and get started on the homework and the lab assignment now. That's going to do it for section 5.5. Thank you.